Hello, my friends, and welcome to this new practical activity on multiple linear regression. So in this new section, we're going to learn together how to build a multiple linear regression model. Just before we start, I just want to make sure that everyone here is on the same page. This is the whole machine learning A to Z folder containing all the code and data sets. And now we should be all on the same page, ready to start this new machine learning model, which is of course in part 2, regression. And now we're going to go of course to multiple linear regression folder, and we're going to start with Python to implement this model. All right, so this is the dataset, and this is the Python implementation in IPYNB format, which you can either open with Google Collaboratory or Jupyter Notebook. Make sure you also have the folder downloaded on your machine so that you can indeed get these files. All right, so before we start the implementation, let me just explain again what this dataset is about. So remember, a venture capitalist fund hired you as a data scientist to train a machine learning model and actually a multiple linear regression model to understand the correlations between these features, which are the spend in R&D, administration, and marketing, and as well as the state, and the profit of what? Of 50 startups. So in this data set, it's very important to understand that each row corresponds to a certain startup, and for each startup, well, you data scientists collected the following data: R&D spend, administration spend, marketing spend, and the state of these startups, and of course their profit. Because the goal for this VC fund is to figure out in which startup to invest based on these informations. So these are all information that we already know from 50 startups, and therefore if you manage to train a machine learning model that can understand well these correlations, well, for the next startup you'll be able to deploy this model on these features to predict what sort of profit this new startup might generate. Okay, so for this fund you definitely want to build an accurate model. All right, and now we can start the implementation. But before we start, I would like you to figure out what are going to be the first steps of this implementation, before I show it to you. All right, so first, I hope that the first thing that came to your mind is that indeed the first step is the data preprocessing phase. And remember, in the data preprocessing phase, we start by importing the libraries, that's for sure. Then we're going to import the dataset, that's even more for sure. And then we will split the dataset between the training set and the test set, because indeed we want to train separately our model and evaluate its performance on a separate test set. Okay, so that's always required. But then, is there something else that we have to do here? Well, to answer this question, let's have a look at the columns one by one. Starting with R&D spend. So R&D spend is a numerical column, containing numerical values. And when we scroll down, we can't scroll down because there are only 50 observations corresponding to 50 startups. And we can see that here there is no missing data. So all good. Then second column, the administration spend. All the spend in administration, like paying employee salaries or anything else. So this column is once again numerical with numerical values, and there is once again no missing data. Perfect. So far, our 3 steps of the data preprocessing template are good. The next one, column in marketing spend, well, same, numerical column with no missing data, all good. And now, this column, the last feature, notice once again that all the features are in the first columns and the dependent variable which you want to predict in the last column. So back to this state feature, what reflex do you have in your mind now? You should have the reflex if you paid attention to part 1 data preprocessing. Basically, the question I'm asking now is, do we need to apply a certain tool of our data preprocessing toolkit, which we built in part 1, into this dataset? Well, here the answer is obviously yes, because indeed this state column is non-numerical. It actually has some categories. It has 3 categories, which are New York, California, and Florida. And therefore, that's exactly the same situation as in part 1 data preprocessing. There is no order relationship between these 3 states, New York, California, and Florida. And therefore, we will have to apply one-hot encoding to that state column. And therefore, we'll have to grab a tool of our data preprocessing toolkit, and that's why I prepared it here, in order to indeed one-hot encode that categorical variable, the state variable All right. And then the profit is fine. It is numerical. And besides, there is, once again, no missing data. So that's what, you must do first. You need to have a look at your data set. If it is not too long, you can check that there is no missing data, like we just did. If it is too long, then I recommend to apply your data preprocessing tool that handles missing data and deploy it on this data set. And then you must check if any feature is categorical. And here we could check that very easily. The state is categorical, so we're going to apply our one-hot encoding tool of our data preprocessing toolkit on the state column. And then, of course, we will apply all the rest of the 3 essential steps of our data preprocessing template. And once again, we will do that in a flashlight because this is a template where we only have one thing to change, which is the name of the dataset. Are you ready? Let's do this. Let's start implementing our multiple linear regression model. So I just double clicked on it. If you like Google Collaboratory, feel free to open this link with me, open with Google Collaboratory. And if you don't like Google Collaboratory, that's totally fine. You can open this file with Jupyter Notebook, but from your folder, which you downloaded on your machine. All right, choose your favorite, and here we go. Let's implement our multiple linear regression model. All right, so first, remember that this file is in read-only mode, which means that we can't modify it. But no worries, we're going to create a copy right away by going to File here and then click Save a Copy in Drive. This will, as you can see, create a copy in which we will be able to re-implement this multiple linear regression model from scratch, because indeed, I remind that this course is an action-based course in which I want you to take action as much as you can, and therefore we're going to re-implement this whole model from scratch together, step by step, and I really want you to code with me at the same time so that the practical skill can really be well integrated in your head, okay? So let's do this. Let's first start by removing all the code cells here, and only the code cells, not the text cells, because I want to keep that well highlighted structure for this implementation. So here I'm just removing all the code cells. There we go, and perfect. So this is the whole structure of this implementation. We can have a look at it here. And indeed, that's why, I wanted to brainstorm on the dataset with you first before showing you the structure in order to make you think what we must do in the data preprocessing phase. And as we said, we need first to import the libraries, then import the dataset, that's for sure. And then here we go, we need to encode the categorical data, and more specifically, that state column, which contains indeed 3 categories. And then, of course, we split the dataset into the training set and the test set. That's a must. And that will close the data preprocessing phase, and we will all be ready to start training, well, first building and then training the multiple linear regression model on the training set. And by doing this, our model will understand the correlations between all these spends of, those startups and their generated profit. And so there we go, we will get a smart model which we will be able to use on new observations, and that's exactly what we'll do as a last step here to predict the test set result. All right, so perfect. So now that everything is essentially set, let's tackle this data preprocessing phase. So we're going to do this very efficiently. I'm going to go to my data preprocessing template, and I'm going to copy paste each of these code cells, the first ones. So I'm creating a new code cell here, pasting that here. That's for importing the libraries. Then we're going to take care of the second step of data preprocessing, which is importing the data set, creating therefore a new code cell here. And let's first take care of this, the last one, the easy one, splitting the data set into the training set and the test set, and pasting that in a new code cell right here. All right. Perfect. And now before we encode the categorical data, let's just make sure to replace what's necessary here in this template. And once again, that's the beauty of the template. We only need to replace one little thing, which is of course the name of the dataset here, right? And the name is of course 50 underscore capital S startups.csv. So there we go. Let's do this. 50 underscore startups. Great, and as a reminder, we don't have to change anything here because this automatically selects all the columns except the last one, and therefore all the 4 features here, so that's perfect. And this line of code automatically selects the last column, which means the dependent variable profit, okay? So once again, we tackled data preprocessing in a flashlight, and now we just have this one last tool to add in our data preprocessing phase, which is to encode that state variable here. So to do this, we're going to get our data preprocessing tools, which you have in your part 1 data preprocessing folder. And now we're going to scroll down to find that tool that, encodes the categorical data. So remember, we actually have two subtools here, if I may say. That first tool that applies one-hot encoding, which is exactly what we want, and that tool that just encodes a binary variable into 0 and 1. And of course, what we need is this one. So I'm just going to copy paste that piece of code, and then I'm going to paste that right here in a new code cell to encode the categorical data. And now your turn to think and figure out what we need to do next. Please press pause on this video and figure out what you have to change here in order to indeed apply one-hot encoding on our dataset. I'll give you a hint. You only have one little thing to change and then you'll be good to go. So please press pause. Okay, and now I'm going to give you the solution. So the only thing that you had to change here is that index here. Remember, this corresponds to the index of the column you want to apply one-hot encoding. And in our previous data set, data.csv, well, remember the categorical variable was the first column. That's why we put index 0 here. But for our new data set, the categorical variable is actually the fourth column. But be careful, remember that indexes in Python start from 0. Therefore, this column has index 0, this one has index 1, this one has index 2, and this one has index 3. And therefore, the index you need to change here is, of course, 3, right? So this will apply one-hot encoding to the column of index 3 in your dataset, therefore exactly this state column. Perfect. So we're done with the data preprocessing phase. So now we are going to observe the results of what we just built, just in terms of data preprocessing. And therefore, we're going to do several things here. First, we're going to upload the dataset into our notebook, right? And to do this, we click this little folder here and then upload. All right, so as usual, my machine learning A to Z folder is on my desktop. So we're going to go inside, make sure to find it on your machine. Then we're going to go to part 2 regression, then section 5 multiple linear regression, then Python. And there we go. That's the data set which we need to open and upload into our notebook. All right, it is uploaded. And now what we're going to do is we're going to run each of these cells that we just made, but I'm going to add a few prints, so that you can really see what we did, how the different matrix of features and dependent variable vector are created and modified along the data preprocessing phase. All right, so first let's start by importing the libraries. That's easy, done. Next step, we import the dataset, and we can now because we have the dataset uploaded in our notebook. So make sure to have it as well. Okay, now the dataset is imported. We have the matrix of features and the dependent variable vector y. Good. And now I'm going to do a print to show you the state of x. What is x exactly at this stage. So I'm going to do print x, and I'm going to run the cell. All right, and let's see what we get. All right, so indeed, we get exactly the same columns as in this dataset, with first R&D spend, then administration spend, then marketing spend, and state, right? We can clearly see that we get the same columns here in the same order. All right, so that's the matrix of features, all good. Now, I'm not going to show you the dependent variable vector because that's obvious. We're going to get the same profit. But what I want to show you is what becomes x after we encode the categorical data, and you can actually guess what it will become, but you will see that the 3 columns resulting here from one-hot encoding will actually be placed at the beginning. All right, so let's check it out. Let's run the cell to indeed apply encoding categorical data. And now let's create a new code cell in which we're going to print x again, and let's run this cell to see what x becomes. And there you go, exactly as I told you, we have the same 3 first columns here, so that corresponds to R&D spend, that corresponds to administration spend, and that corresponds to marketing spend. But now, instead of having this state column here, we indeed have these 3 new columns at the beginning encoding that state variable. And we can actually see what corresponds to what. If we have a look at our data set, well, the first row has New York as the state, and therefore New York was encoded as 0, 0, and 1. then let's see, as a second state of the second row, corresponding to the second start, we have California, and therefore California was encoded as 1, 0, and 0. And finally, well, Florida was encoded as 0, 1, and 0. All right, so that's the one-hot encoding that happens. And now, all good, we have a fully pre-processed data set. And as I told you in part 1, but I'm going to say it again here because this is important, we don't have to apply feature scaling. And one last thing I would like to add as well, because I know a lot of you asked this question, do we need to check the assumptions of linear regression? The answer is absolutely not, because I will explain at the end of this part, part 2 regression, that whenever you have a new data set and you want to experiment with some machine learning models to figure out which one leads to the highest accuracy, well, even if your data set doesn't have linear relationships, you can still try a multiple linear regression on it. And if you know your data set doesn't have linear relationships, well, your multiple linear regression model will just perform poorly, and therefore it will get an accuracy lower than the accuracies of your other model. So you will just not select the multiple linear regression model, but you don't have to check the multiple linear regression assumptions. It will just be a waste of time. Really, I will show you at the end how you can so fast and so efficiently try each of the models on your dataset and select very quickly the one that has the highest accuracy. All right, so I just wanted to be clear on that point. Don't worry about the multiple linear regression assumptions. If your dataset has linear relationships, then good. Your multiple linear regression will check the assumptions indeed and will bring to you a high accuracy. And if your dataset doesn't have linear relationships, well, fine, your multiple linear regression just will perform poorly and you will just take another model. And that's it. That's as simple as that. All right, so now good. We're done with data preprocessing. We can therefore move on to the next step, which is to train the multiple linear regression model on the training set. Now we're ready for the exciting step, which is to train the multiple linear regression model on the training set that we now collected thanks to the previous step. But first, before we do this, I would like to answer two important questions. The first question is, do we have to avoid, to do something to avoid the dummy variable trap? And the answer is no, because indeed the multiple linear regression class that we're about to import and which will build the multiple linear regression model itself and actually also train it, because remember that a class actually can complete several actions, including building it and training it. And well, this class will automatically avoid this trap, which means that indeed, one of the three first columns here, because remember, Kirill explained that one is redundant, well, will automatically be outcast. So you have nothing to worry about regarding the dummy variable trap. You don't have to remove one of the columns here. And that's the beauty of classes. These are advanced implementations that allow you to build a model, a machine learning model, in just a few lines of code. And this will take care of the dummy variable trap for you. Now, second question, do we have to work on the features to select the best ones with, the techniques that Kirill introduced to you, like, for example, backward elimination? Do we have to deploy the backward elimination technique in order to select the features that have the highest p-values and that are the most statistically significant? And the answer is, once again, no. Why is that? Well, for the exact same reason as the dummy variable trap. The class that we're about to call to build our multiple linear regression model will automatically identify the best features, the features that have the highest p-values or that are the most statistically significant, to figure out how to predict the dependent variable, the profit, with the highest accuracy. So once again, you don't have to worry about this. The class of scikit-learn, this amazing data science library, will take care of everything for you. Okay? So I'm glad I answered these two questions. The purpose of building machine learning models today is to be efficient, because in your career, I can't tell you how many times I had to test several machine learning models on my data set and select the best one. Well, if I had to deploy the backward elimination technique on my data set, well, I would have lost a lot of time. And here we have a class that takes care of everything. You just have to deploy your class on your dataset, and then you will get an accuracy, and you will compare that accuracy with the accuracies of other models. And that process is called model selection. That's what we actually cover in the part 10 of this course. So really, I want you to be efficient with your implementations and your machine learning toolkit so that you can optimize your model selection process. All right, so now that we said this, well, let's build together the multiple linear regression model. And now actually I have some good news because, we're still doing linear regression. And in the previous section, we actually did simple linear regression, with which we therefore had one feature in our dataset. And now we're doing multiple linear regression, which is exactly the same as simple linear regression, except that we have several features. So the good news is actually that the class that we're about to use to build and train this multiple linear regression model is actually the exact same class as for the simple linear regression model. It will just recognize that there are several features and therefore that we are doing multiple linear regression, but the rest will be exactly the same. It will be trained to understand the correlations between all your features, actually I can open it here, all your features and the profit, which is your dependent variable, and then it will take care of the dummy variable trap, and it will also take care of selecting the best features that are the most statistically significant. So that's the good news, but still, I just want to re-implement this again from scratch to make sure it is best integrated in your head. All right, so let's close this and let's implement our multiple linear regression model. Actually, try to do it faster than me. Try to do it before me. You can press pause on this video and do it. And me, I'm going to do it pretty efficiently. So remember, we have to start from the sklearn, the scikit-learn library, from which we're going to get access to this specific module, which is linear model. There we go. Google Colab guesses it perfectly. And from this module, we're going to import, well, the linear regression class. Google Colab guesses again perfectly. All right, so that's the exact same class as in the previous section on simple linear regression. And there you go, we're going to do just exactly the same. This is exactly the same code as what we did in the previous section, because now we're going to create a new variable, which will be our multiple linear regression model, which will be created as an object of this linear regression class. So let's introduce this new variable, regressor, equals, well, since this will be an object of the linear regression class, I'm just copying this class and pasting it here and adding some parentheses. All right, so that regressor is created as an instance of this linear regression class. Now the question is, do we have to enter any parameters here? Well, just like simple linear regression, the answer is no. We are just going to keep the default values of the parameters inside this linear regression class. I will explain in a whole section parameter tuning, when you can improve your model, but for linear regression it's pretty simple, so usually we don't have anything to input here. And now final step. With this line of code, we actually built the multiple linear regression model. So we have the model already, only right now it is dumb. It is not trained yet on the dataset. So now we're going to make it smart by training it indeed on our training set composed of, remember, X-train and Y-train. So there we go. Let's take our regressor object, from which we're going to call the fit method, which takes as input, right, exactly the same as before. First, the matrix of features X train, and second, the dependent variable vector Y train of the training set, of course. All right, and that's it. This line of code will build our multiple linear regression model, and this line of code will train it on our training set. All right, perfect. So now let's just execute the cell. So let me check the cells that we didn't execute before. So we executed everything up to here. So we still have to execute this cell, to split indeed the dataset into the training set and test set. And now we have the training set, and therefore we can proceed to this next step to train the multiple linear regression model on the training set. So here we go, let's do it. Clicking play, and there we go. We now have a fully trained linear regression model on this dataset. So now we have a model that was trained to understand the correlations between different types of spends by 50 startups and their profit, so that now investors can deploy this model on new startups in order to predict what profit they will generate based on these informations. All right, perfect. So congratulations. Now let's recap, 3 things. thanks to this amazing linear regression class, you don't have to worry about the dummy variable trap. You don't either have to worry about selecting the best features, meaning the features with the highest p-value or the most statistically significant. The linear regression class will take care of that as well. And also, you know how to build and train a multiple linear regression model on a dataset, which you also know how to pre-process like a pro. All right, so we're now going to move on to the last step, which will be to predict the test set results, because remember that so far our model was trained on the training set, and therefore we still need to check its performance on new observations, which are contained in the test set. However, here we have to understand something important, compared to what we did in the previous section on simple linear regression. This time we actually have several features, right? We actually have 4 features instead of 1, like before. And therefore we cannot actually plot a graph like we did in simple linear regression, where, we have the features in the x-axis and the dependent variable in the y-axis, because simply there are 4 features. We would need actually a 5-dimensional graph, which is not possible to visualize as humans. So what we're going to do instead, instead of visualizing the test set results on a plot, well, we will actually display 2 vectors. The first one is the vectors of the real profits in the test set. And remember that the test set actually counts for 20% of the whole data set. And therefore, since here there are, actually 50 observations corresponding to the 50 startups, well, 20% of 50 will be 10 observations in the test set. So we will actually have 10 samples in the test set, and we will display 2 vectors. First, a vector of the 10 real profits from the test set, the 10 ground truth, and a second vector of the 10 predicted profits of the same test set, so that we can compare for each startup of the test set if our predicted profit is close to the real profit. And that's how we will, evaluate our model. And then later on in this part, you will actually learn about some evaluation techniques to measure better the performance of your regression models with some relevant metrics. But so far, this is how we will do it. We will clearly see if, our model performs well on new observations, on the test set, because we will clearly see if the predictions are close to the real result. Okay? So you can try to do it yourself, at least the first step, which is to get the vector of predicted profit. But then in order to display the 2 vectors, next to each other, well, we'll have to use some certain tricks which are not necessarily obvious. So we'll do that together. All right, let's do this. Let's predict the test set results. So as I said in the previous tutorial, we're going to display 2 vectors. First one being the vector of the real profits in the test set, and the second one being the vector of the predicted profits in the same test set. And we're going to compare next to each other to see if our predictions are close to the real results. All right, let's do this. Let's start by creating a new code cell. So the first thing I asked you to do was to indeed get that vector of predictions. So first, since we want to get a vector, I'm going to introduce a new variable, which I'm going to call, as usual, ypred. So that's going to be the vector of the predicted profits in the test set. And now, how do we get our predictions? Well, you know the solution. It's actually exactly the same as with simple linear regression. We first need to take our regressor object, our multiple linear regression model, from which we're going to call that predict method. And of course, in this method, we have to input the features of the test set, exactly these ones, not including the profit, of course. These are all the features with first the encoded variables for the state, then the R&D spend, then the administration spend, and the marketing spend. All right, so these are all the features which we need to input in our predict method here in order to predict the profits. So let's do this, x test, and there you go. Now we get our vector of predicted profits. Perfect. And now the next step, the thing that I'm going to do is I'm going to call numpy, which has a shortcut np, from which I'm going to call one of its functions, which is set underscore print options. And now in the parenthesis, I'm just going to enter precision equals 2. All right, and this will display any numerical value with only 2 decimals after comma. All right, so this will be much more beautiful to visualize and mostly much easier to visualize. Okay, good. And now final step. This is a step where we're going to display the 2 vectors of the real profits and of the predicted profits together next to each other. And to do this, well, we're going to use A classic trick with NumPy, concatenate. Concatenate is a function of NumPy that allows to concatenate either vertically or horizontally two vectors or even arrays. And so now we're going to use the concatenate function to concatenate vertically our two vectors of the real profits and the predicted profits. All right, so let's do this. Just follow me. I will explain everything as I'm coding. So first, we're simply going to start with a print, because we want to print that concatenation of the two vectors. Then, here we go, we're going to call that concatenate function by NumPy, from which, there we go, we call the concatenate function. Perfect, parenthesis. And now be careful, because this is always a bit confusing. The concatenate function by NumPy actually expects as a first argument, check this out here, the tuple of arrays you want to concatenate, or, vectors. So actually all the description is here. A1, A2 is a sequence of arrays you want to concatenate, and that must have the same shape. Well, that's perfect for us because, of course, our vector of predicted profits and the vector of real profits have exactly the same shape, meaning they are a one-dimensional vector containing the same number of profits. Okay, so that's good. But these vectors that we want to concatenate have to be in, some parentheses, and these are actually the first argument. This tuple of arrays or vectors is the first argument input in parentheses. So here I'm going to add new parentheses. All right, this is the first argument. And what is going to be inside these parentheses? Well, of course, are two vectors, the vector of predicted profits and the vector of real profits. All right, so let's first add the vector of predicted profits. This is, of course, ypred. And now, because we want to display them vertically and not horizontally, remember that, actually I can show this to you in data preprocessing tools. We actually printed y at some point. There we go. Remember when we print the dependent variable vector, since it is vector, it is displayed horizontally. I actually prefer to display, our two vectors of predictions and real profits vertically. So now I'm going to add another trick to put that vertically, to convert that from being horizontal to vertical. And the trick to do that is just to add dot reshape. Reshape is an attribute function that allows to, reshape your vectors or arrays. And in order to reshape a vector from being horizontal to vertical, well, we just need to add as input of this function, first, the number of elements in ypred, and that's actually so far the number of columns because, it is horizontal. And to get that number, we can simply use the len function, which returns the length of a vector. And therefore here, I'm going to input ypred. Okay, so this is the first element of the reshape function, and the second one is just 1. All right. So what does that mean? That means that you want to reshape your ypred vector into an array having len ypred rows, meaning that the number of rows will be equal to the number of startups, and then just one column. All right, that's what it means. So it's good that you know this reshape trick. Now you know how to reshape your vectors, and you will see that it is actually going to be much nicer. And now, next one is going to be, well, the other vector we want to concatenate to that vector of predicted profits, which is the vector of real profits. All right, so here we can do this very efficiently because this is exactly the same trick. I'm going to copy all this and paste that here and just replace ypred by, what do we have to replace ypred by? Well, of course, we have to replace it by ytest, because ytest contains, of course, the real profits in the test set. All right, here we are evaluating our model on the test set. So here we go, replacing ypred by ytest, and here as well, actually we could keep that because the length of ytest is the same as the length of ypred. But there we go. Now we have a beautiful concatenation of two vertical vectors. But remember this, this up to here is actually the first argument of the concatenate function, and therefore we need to add the second one, which is the axis, as you can see. So axis here can take two values, 0 or 1. 0 means that we want to do a vertical concatenation, and 1 means that we want to do a horizontal concatenation. And since here we want to concatenate two vertical vectors together, well, that concatenation is actually horizontal, and therefore we have to input here axis equals 1. And we don't have to specify the name of the argument because this is input in the same order. All right, okay, good. So now we're going to observe the final result and see if our model was able to return some predictions, some predicted profits close to the real profits. So there we go. Let's press play to run the sale, and awesome. I didn't make any mistake. Perfect. So let's recap. We can clearly see that we have two vectors here. That's the first one, and that's the second one. On the left, we have the vector of predicted profit, so that's ypred, and on the right, we have the vector of real profits for, of course, the 10 startups of the test set. All right, and so let's see what we get. Let's see if our predicted profits are close to the real profit. So for the first startup of the test set, well, the predicted profit is around 103,000 and the real profit is actually 103,200. So very close. That's perfect. That's an amazing first prediction. Then second startup of the test set, the predicted profit is 132,582 and the real profit is actually 144,000. So not a great prediction like before, but still not too bad. Third startup, 132, 146. Still not great, but not too bad either. Fourth startup, 71, actually 72 and 78. All right, so pretty close. Then 178, 191, okay. 116, 105. So actually the first prediction was amazing, but then, the other ones are still quite good. Then 67, 68, actually 81, okay. 98,000 and 97,000, very good. 113,000, actually 114,000, 110,000, very, very good. And 167,000 and 166,000, amazing predictions. So we have some, amazing predictions, very close to the real profits, and some okay predictions, okay-ish, that are not too far from the real results. So here, from what we see, well, we could say that the multiple linear regression is well adapted to this dataset. The dataset does not necessarily have some perfect linear correlations. However, you can be assured that with this linear regression class, well, it was able to select the right features with the right parameters to make these predictions. And even if you tune your linear regression model by, for example, applying backward elimination to select, a team of more statistically significant features, you will actually get similar results. You can try that, actually would be a good practice. We actually do that in the R section, but in terms of performance, this won't change much. And remember, your goal is to be efficient when building and testing your machine learning models. So when you get such results with your multiple linear regression, in real life, you will actually try other models. You will actually try other modules, which you can tune also. And then in the end, you will compare the performance of each of these models and select the best one. So we'll talk about this again at the end of this section, and also a lot in part 10 on model selection. And so now I have to say congratulations, because you now know how to build another machine learning model, which is multiple linear regression, and therefore which you can add in your toolkit thanks to this new code template. Perfect. So now we're going to move on to R. I remind that you don't have to master the 2 programming languages. If you want to master the 2, that's fine. Join me in the R tutorials. And otherwise, if you want to stick to Python, well, feel free to skip the R section. In the next section, polynomial regression, where you will learn how to make predictions on a non-linear dataset, on a dataset with non-linear relationships, therefore with which a multiple linear regression model would not be relevant. So it's an absolutely necessary model to add in your toolkit, and you will add it in the next section. Until then, enjoy machine learning.